Hello everyone, welcome back. In previous video we said that metallic crystal structure will be divided into four structures: simple cubic, FCC or SC, FCC, BCC, HCP, which is face-centered cube, body-centered cube, hexagonal closed pack, and simple cubic. So we'll start with simple cubic. We'll explain each of them one by one. Now we have to understand the arrangement of atoms, how they are, and some properties related to this crystal structure. The first one is simple cubic. Simple cubic crystal structure is, they call rare. Why? Because they're low packing density. We have it, low packing density. So it's rarely elements they will go for this, they will arrange themselves in this manner. They don't like it. Why? They want to be dense, so we go for the other, they will go for the other crystal structure. For example, if you look at the 3D, so there is two way, there are a lot of example, I put it here to understand the crystal structure. Now polonium is one of them that has, the only polonium has this crystal structure. There's no, the others, they don't prefer, they're not gonna come with this crystal structure. Why? Because look at the inside here. I'm not sure if you see the cursor. Inside here there is a lot of space, empty spaces there. So they don't want to be like this. Sometimes they will put an atom in the middle here, so the arrangement will change. That's gonna give us different crystal structure. This is, so we have different way to imagine this crystal structure. Now we're not going to use this, let's bring the cursor. We're not going to use this one. We're not going to represent the crystal unit cell in this manner for our calculation, but this is how it looks like. Four atoms, one atom at each corner of the cube that we have it. By the way, before going further, those crystal structure that we will explain in them here, all of them are, this is cubic, or this, the name is clear, hexagonal, this is also cubic, So the cube basically, the lattice that we have it's cube. The lattice system that we have it's cube here. Why? Because we have other lattice systems. So let me just show to you the other lattice. It's better to see them before further. So the lattice parameter, this is cubic. Cubic, you know that the sides are the same, the angles 90. We will discuss hexagonal as well, but we're not gonna go too much detail for the other one. For example, tetragonal, it's what you have, the bottom are the same but the height is different, still the angle 90. Or trigonals, or the other one, orthorhombic, monoclinic, triclinics, each of them are a different systems that we have them, a different system. We may have, like we said what? We said a simple cubic, yes? Simple cubic. Theoretically, you can say simple, not cubic, something else. Theoretically, it might not be available, but you can say, for example, simple orthorhombic. Instead of say simple cubic, you can say simple orthorhombic. It means that you have one atom at each corners, or simple monoclinic, so one atom at each corner. So there is two terms that you're supposed to understand. There is one which is the crystal structure. The second one is the system or the lattice, or the lattice parameter for a crystal system. There's two terms appearing, so it's better to differentiate them here. There is crystal system, and there is crystal structure. Crystal system and crystal structure. Crystal structure talking about the atoms arrangement of atoms. However, crystal system is the shape of the lattice. For example, this is cubic, this is hexagonal, this is tetragonal, and so on. It's not telling us where are the atoms arranged. No, crystal system, it's the lattice arrangement, the lattice shape. However, crystal structure, it's the arrangement of atom. So when we said crystal structure, look, we mean about the arrangement of atom. One at each corner. Imagine you can simply bend this one, yes? I mean, even if this is not a cube, we can still have the same arrangement. Imagine that you have something like this. If I can create it, let's say this way. Put an atom at each corner. I cannot make it bigger than this one. I will still end up having a simple structure. But I cannot say simple cubic because the arrangement will not be, I mean, the lattice is not unit, it's not cubic. Maybe this is one of the other systems, so I can still say simple and the name of the system. For example, simple orthorhombic or simple triclinic. So whatever the system comes will be the name of. So we will dealing with what? Cubic for most of the calculation that we have. We'll deal with cubic system. Now what do I want from each of you? I want you to visualize this crystal structure. Now this is the arrangement in a 3D that we have it in a 3D. So the atoms will be at the corner. We don't have anything in the middle. We don't have anything in the face. Remember, this is what we call simple cubic crystal structure. There's a lot of way that explained for you. One at each corner. Now, this one is mainly used for the purpose of our calculation. Now it's somehow sliced up, yes? Sliced. Why? Because when you see a unit cell, look at this, one of them. Let's say look at this atom here, number 1. For example, this atom here. This atom here, it's at the corner, yes? But the corner of what? If you check, this is a cube, yes? Am I finishing? If I draw the cube here, it's gonna come here. This is the cube we have it, yes? Let's use a line here. Easy. Sorry. Let's make it easier. So if I draw a unit cell, this is the unit cell that we have it. So I'm going to explain the relation between adjacent unit cell that we have it. I mean, this is a unit cell. And also we have another one, yes, and another one. So if you go in this manner, you can see that in an atom will be shared between where? Why? Because we have multi-unit cell around it. So I can just make them different color to represent the top So I can create this unit cell by repeating the same manner. Now the one in the middle is the easiest one to understand this, why we have this shape of the, why do we have this shape here? I mean, this is why it's not a full sphere here, a full sphere. Why we only have this, a part of the sphere? This is because an atom, a corner atom, look, remember this one, a corner atom, it's shared between 8 unit cells. A corner atom shared between 8 unit cells. Imagine here, look, checking this one here, this one here. One, this is a unit cell, this is a unit cell here, there's a unit cell here, there's a unit cell here, and 4 at the top, yes, 4 at the top. So that's why this atom shared by 8 unit cell. Taking one, there's 4 here, there's 4 at the top as well. Any one that you take it, there will be 8 unit cell taking advantage of that atom. So that atom will be divided by 8. 1/8 of the atom. That's why this is 1/8 of an atom, because it's not full inside the unit cell. When we say a unit cell, we consider this anything within this cube, not outside of it, not outside of it. So anything within this cube we need it, not outside. So this atom here will be sliced into 8 parts. Each part will be given to one of the, each part will be given, for example, one part will be given to this unit cell, one to the other one there, one for this one here, and one for the one I'm facing it, and then also to the bottom, the way we have it, there will be 4 for the 4 unit cell at the bottom. So that's why each corner atom will be divided by 8, and a portion will be given to the unit cells. That's why this is how we're representing a unit cell for our calculation. Yeah, this is, we call it reduced sphere, reduced one. This is the actual one. This is the actual one. This is we call reduced sphere, to explain that, okay, we have atom at each corners, but we're gonna use this one for the calculation mainly. Why? Because A is the cube side, yes. A, we call it lattice parameter, as we said that we have 6 parameters to represent the systems. Remember? Here we said that we have 6 parameters to represent a system. A is one of them. A, B, C, alpha, beta, gamma. In the cube we said that A, B, C are equal, and alpha, beta, gamma, they are 90. That will be cubic. That will be cubic. So when you say lattice parameter, it means, it means that parameter that are representing the system. If it's cubic, you only have one lattice parameter, which is A. Why? Because alpha, beta, gamma 90 and A, B, C will be equal, so we only have A to represent cubic system. But the other system, they might need more than one lattice parameter to be defined. Now, can I find the relation between the lattice parameter and the radius of the atom? Yes, because the arrangement here is providing this information. Now, let's understand from here again, come back to this part here. We have an atom at the corner, another atom at the corner. So the distance between this atom to this atom basically will be 2r. Why? Because they're touching each other. The center toward here it's r. I mean, from this center to the surface again will be r. So from center to center, which is the corner to corner, will be 2r. So we will exactly understand that. Now the lattice parameter here, is equal to 2r. R stands for the radius of the atom, radius for these atoms, and because we have it in this manner, the atoms touching each other. Since the atoms touch each other, it means that from the center toward the surface will be radius, on the other side radius, so the lattice parameter will be 2r. The lattice parameter will be 2r. So this is r. So imagine this is going to be r here, and there is another one from the center toward here. So that's why lattice parameter A in a simple cubic structure is equal to 2r. R is the radius of the element. So if I want to calculate the density of this one, if I know the element, I can calculate the density or the volume. So we're going to come back to this one. And this is how a chemist Mendeleev basically calculated density and those things. Theoretical density we call it. We will show it to you. If I know the crystal structure, we can calculate theoretical density. We will discuss this one in detail, or the way that the void and the density of this one, we call them another term, atomic packing factor, how much those atoms are packed together. We will have this one as well. So in each crystal structure, I need you to imagine the way that the atoms arrange themselves. Why? Because this is very important. All this chapter depends on your imagination to have in your head the way that those crystal structure. Now when someone says a simple crystal structure, what I have to know, in a simple cubic crystal structure, I mean, if you don't say even cubic, even if you don't say cubic, it's enough to say simple crystal structure. In a simple crystal structure, the atoms will be at each corner of the lattice. So if it's cubic, at each corner of the cube we have one atom, and the atoms are touching each other. The way that we explained here, they're touching each other, and that's going to provide us an information that the lattice parameter here, for example A, the lattice parameter A will be equal to 2r. And another information that we know, that at each corner we have one atom. Yes, we have one atom, but this unit cell is gonna take 1/8 of this unit cell will take 1/8 of the corner atoms. 1/8 of the corner atom. So let's say the calculation that we have it here. This is the lattice parameter. The edge of the cube is equal to 2r. A is equal to 2r. We'll talk about coordination number. Number of atoms per unit cell. This is important. Number of atoms per unit cell. Why? Because we said that each corner, this is what, at each corner we have 1/8. 1/8 of atoms. It's not full atom, because we said that one atom will be shared between 8 unit cells. So 1/8 will be for this unit cell. How many corners do we have it here? We have 8 corners. Yes, 8 corners. So if you collect all of these corners together, you will have one atom, because 8 corners we have. So 8 times 1/8, 8 times 1/8, we're gonna have one atom. So how do we represent this one? We will not say that we have 8 corners, each corner is 1/8 atoms. We will say that number of atoms inside, when you say inside, it means that within the cube, it's equal to 1. One atom within this cube. I mean, it's not I've seen students, they do it like this. They say, okay, sir, you told us that there is one unit, one cube. Let's make this one. They'll tell me, okay, what they do, they say, okay, sir, you said that there is color. You said there is one. If I draw a 3D, colors became different. It's okay. Let's say this is the cube in a 3D. We say that there is one atom, but it does not mean that you'll just simply go and put one atom directly in the middle. It's not like this. There's no simple cubic. Yes, we have one atom. I mean, if you sum the corners together, those corners gonna give you one atom. But the atom is not in the middle. It's not in the middle. I mean, 1/8 of the atom, 1/8 of the atom, it's at the corners. At the corners. So, when we say number of atoms per unit cell, n is equal to what? That is explained here. So we have eight corners, and each corner we know that is 1/8, because why? A corner atom will be shared between 8 unit cells. So one portion will come for that one, and we have 8 corner. That's going to be having one atom inside the crystal, inside this unit cell. Inside this unit cell we have one atom. I mean, the summation of those corners give me one atom. Why we need to know this one? For the volume, I mean for the density, because if I know the radius of the elements, I know that the summation of those atoms, corner atom, will be one atom, so I can calculate the volume of one atom. Why? Because it's a sphere, and we know how to calculate the volume of sphere. And we're going to show it to you in calculation how we do these things. There is another number, I mean another term that we will have it, coordination number. Coordination number. This is we call the number of closest atom touching. Now if you take one atom here, one atom, there will be 6 other atoms touching, I mean they call the neighbors, touching this atom. This is not clear within this 3D. It's clear if I had an, let's see if I can explain this coordination number somewhere else. Not this simple cubic. I think we don't have simple cubic in. Yes. Basically, yes, we don't have simple cubic here. Yes. We don't have simple cubic. The coordination number here, they're different. So it's basically representing of, yeah, well, let's see. We said that this is, we open up in this manner. I mean, they are close to each other. This atom basically is somewhere here. They are, okay, let me put them beside each other. That will make sense in that case. If I put all of this atom beside each other, I mean, bringing what? I brought this one down. It's like this. It's not at the top, because we say they're touching each other, yes? So each atom, if you take it, for example, this one here, it has 6 neighbors. 6 neighbors. Why? Because one at that side is touching, one here, one at the top, then it will go for one at the bottom, one in this direction. Why? It's continuous, one in direction. That's what we call coordination number. Is the number of atoms that are touching each other, the closest neighbors to which the atom is bonded. Or we call them, you can call it bond, because they're touching each other, there will be bond between those atoms there. So the coordination number for simple cubic will be 6, because each atom having 6 neighbors. The way that it's arranged. So it's all for what? In order to understand how the simple crystal structure, or you call them primitive crystal structure, arranged. Because if you know the coordination number, you'll be able to know the bonding, the way that those are will be links to the atoms. I will leave the atomic packing factor for another video. I'm not going to explain it here. So this is mainly the information that we need to know. Let's just summarize it on a simple cubic crystal structure, or some books they call P, stands for primitive. It's the rare crystal structure. Atoms are gonna go for the corner of the system. If it's cubic, so will be one atom at each corner, and each atom will be shared between 8 unit cells. Atoms are touching each other alongside of the lattice parameter, the lattice parameter A, and we say there is a relation between the radius of the atom and the lattice parameter, because the atoms are touching each other along the edge, so we call a lattice parameter is equal to 2r, and r goes for the radius of the sphere of those atoms. If I know the element, I will know the radius. If I know the radius, most probably I know the atom. Then this is we're going to explain to you at the end of this chapter, those crystal structures. I mean, how do we know which kind of material we have? I mean, when they find a new material, how do they know which material is it? I mean, they go with techniques. We're going to explain it to you. We will find a crystal structure. If you find a crystal structure, you'll find the radius of the elements, and if you find the radius, you know which element it is. So this is a technique that we're going to show it to you, and you have to understand it as engineer wherever you go. When you want to know a material, you simply do this experiment, and with this experiment you're going to gather some information, and we're going to teach it to you how to use those techniques in order to be able to find the elements. Why? Because any material that you have, it consists of some elements. So which elements they are, how do we know them? Sure, each element they have their own properties. We'll be able, one of the properties, that radius and arrangement of the atoms as well, is going to give us some lightnings in order to define the material. So we need to know those information on each crystal structure. So in the next video we're going to talk about the others, the arrangements. Remember the arrangements, the relation between the lattice parameter and the radius. The coordination number, we might not have too much calculation or base to this one. It's just simply the way that the atoms are bonded, or the neighbors, closest neighbors to that each atom. That will be. Now this is important. We said that how to calculate number of atom inside a unit cell, or the volume of the atom. It says in that way, because you have 8 corners, each corner will be 1/8, and that 1/8 came from where? By understanding that each atom will be shared between 8, 3, 4, 5, 6, 7, 8 unit cell. That's why it will be divided to 8 portions. Each portion will go for 1 unit cell. Thanks for listening.